Did you ever want to become a hacker? In this video, I will show you how to become an IP hacker. Remember the character Neo in Matrix? You're going to be able to see the world in a binary code, and you're going to be able to dodge bullets, metaphorically speaking. Let's roll. Welcome to CCNA 200-301 course. Today, we're starting a new section, Section 3, Part 1, IP addressing and routing. Today's session is all about IPv4 subnetting. Here are the topics I plan on covering today. We'll first discuss IP overview. We'll then get into IPv4 binary to decimal conversion. Then talk about IPv4 private versus public addresses. And finally, I'll wrap it up with IPv4 subnetting. Let's go. First, IPv4 overview. IPv4 is the most widely deployed protocol globally, and that's the dominant protocol on the internet today. IPv4 is defined in IETF publication RFC 791. So if you Google RFC 791, you're going to come across the original specification of IPv4. It was published in 1980s, I believe 1981 to be exact. And it's been around since then. Let me quickly touch base on IETF. IETF stands for Internet Engineering Task Force. They've been around a long time as well. It's an open standards organization based in the United States. They're located here in the Silicon Valley, and they're responsible for the enhancements to the TCP/IP protocol. And IPv4 happens to fall within that realm. IP address is a 32-bit long binary string, and I'll show it to you in a moment. But a couple of things to keep in mind. You have to read it from left to right, very much like mathematics. Total number of IP addresses provided by IPv4 address space are 2 to the power of 32, or 4.3 billion roughly, give or take. Now, given the current population of 7.8 billion people globally, you may think that this is not nearly enough number of IP addresses to be able to serve all the people on planet Earth, given the fact that over half of the world's population today happens to be on the internet. Well, you would be correct in thinking so. We're actually running out of IPv4 addresses, believe it or not. However, there are some interesting techniques and hacks that we can use to extend the life of IPv4. We'll talk about that as well. An IP address is divided into 4 different octets of 8 bits each, or 1 byte each. 8 bits equal 1 byte. And let me show you in a moment what an octet looks like. But the word octa comes from Greek, and octa means 8. So 4 octet naturally means 4 pair of 8 different values of binary, and each decimal number is 1 byte. That means it's 2 to the power of 8, or 256, and the decimal range starts from 0, goes up to 255. And let me show you what I mean. If you look at an IP address, you may find an IP address that looks like this, 192.168.10.1. It's also known as dotted decimal format. And if you were to look at the binary of this IP, that's what you're looking at the bottom here. So let me explain. If I can go slightly deeper here, you see this 192 here and this IP address. This right here is translated to this binary code at the bottom in the first octet. And each octet is delineated by a dot. As you can see, there are 3 dots, right? And you can see the same dots down below. Up at the top, we have the decimal format, which we're familiar with, right? But computers understand binary. And that's why we need to understand binary as well, because we need to understand the binary math in particular to be able to deal with IP addressing. So as I mentioned, first octet 192 translates to 11 and a bunch of zeros. Then the next one, the second octet, translates to 168. That is 10101 and a bunch of zeros. And then the third octet is 10. And this translates to a bunch of zeros followed by 1010. And then the final and the fourth octet, which happens to be 1 in decimal, it translates to a bunch of zeros followed by a 1 in binary. So as you can see, in binary, we can only have either a 0 or a 1. That's what binary means. You're either off or on. 0 in binary means off, and 1 in binary means on. Now, if you feel a little lost at this point, let me help you out here real quick. So what we'll do is, on my Apple Mac Mini, we'll go up to the top, Apple menu, top left, go to System Preferences. We'll then click on Network and click on Wi-Fi, Advanced, and then finally click on the tab TCP/IP. And what we're looking at here is the IP address that's assigned to this machine, along with a subnet mask and a router. Now, why is this important? Well, the reason I believe it's important to talk about this quickly is the fact that I guarantee you, pick any device in your network at home and it has an IP address. And specifically, as you can see here, it says IPv4 address, right? And then there's a subnet mask and the router. But the bottom line here is every single device on your network has an IP address in your home or your office or any other environment where you have devices connected to the internet or to a network. They must communicate via IPs. That's why it's important and relevant to understand IP addressing. And hopefully this provides a real-world perspective on this. Now back to IPv4 overview. Now each IP address is accompanied by a subnet mask. And without a subnet mask, IP really doesn't give you any information. So it's almost a requirement that you understand the subnet mask when you're looking at an IP. So here's an example. You got 192.168.10.1, and the subnet mask is right below it, which is 255.255.255.0. And what this does for us when we have a subnet mask, it helps us differentiate and delineate between the network portion of the IP and the host portion of the IP. Hang in there with me. If it doesn't make a lot of sense right now, do not worry. By the time you're done with this video, you will be a master of looking at IPs and being able to make sense of what these numbers actually mean. So just to kind of reiterate, we got this IP address and we got the subnet mask down below. As you can see, the first 3 octets here in this case, octet number 1, octet number 2, and octet number 3. Same thing. Octet 1, octet 2, octet 3. Up here we have an IP address. Down below we have a subnet mask. Okay, just to be clear. And when we look at these 3 octets, the first, second, and the third, that makes up the network portion for at least the address you're looking at. It's different for different types of IPs and different types of subnet masks. But in this case, what we have is a network portion that is the first 3 octets and the host portion that is the last octet. IP address can be classful or classless. And I'm going to go deep into this topic so you understand what that means momentarily. Classful means when the original IPv4 RFC came out, RFC 791 that I was talking about on the last slide, it had 5 different classes specified within it. Class A, Class B, Class C, D, and E. And we'll talk about all these classes in a moment, but that's what the original RFC 791 defined in its specification. However, before I start talking about the different classes of IP addressing, what we need to talk about first, I believe, which would make it a lot simpler for you to understand things going forward, would be a quick look into the binary to decimal conversion for IPv4. This is a key concept, guys. This is the most fundamental and key concept when it comes to layer 3. If you guys do not get this concept, you guys will struggle with layer 3. And layer 3 is the heart of routing. Routing happens at layer 3. So you need to understand it. If you want to become a world-class engineer, you must understand how routing works, how IP addressing works. Let's take a look. So we have this conversion chart that I'm going to show you here in a moment. It helps us convert from decimal to binary and binary to decimal. We can kind of go back and forth. And each bit position in an octet has a decimal value associated with it. So for example, what we do is we actually draw this out. So remember we talked about 8 bits, which equals 1 byte. So an IP address, when we look at, let's say for example, 192.168.1.0. When we look at this, each octet, this is the first octet, this is the second octet, this is the third octet, and this is the fourth octet. Each octet is 8 bits. 8 bits per octet. If you were to kind of chop up an IP address into different octets like this. And if you were to zoom into one of these octets, let's say we zoom into this first octet, that's 8 bits. Well, if we can lay them out like this, okay? Starting with the value 1, 2, 4, 8, 16, 32, 64, 128. The idea is that these values double, as you can see. They're doubling as we go from right to left. And it will make more sense when I show you that in binary, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. So on and so forth. And when we have all the bits on, what we end up getting is what's called a broadcast address. And a broadcast address is an address that's sent to all the devices on the network. Whoever is within that subnet that you belong to, every single device in that network is gonna get that message. Hence the name broadcast. It's similar to, if you guys recall, in layer 2 when we were discussing, when an ARP gets sent out and you have all Fs at layer 2, if you guys recall, it's the same thing, but at layer 3 instead. F, all these different Fs happen to be at layer 2. That's the layer 2 broadcast, right? And for us at layer 3, 255 is the broadcast. It's the equivalent. It's the same thing. And what we have next is all zeros. That is considered a network address. So in other words, this defines the beginning of an IP address range, and this defines the end of the IP addressing range. Now let's quickly jump into the IP address classes. So if you guys recall, there are 5 different classes, A, B, C, D, and E. Let's first quickly take a look at Class A. What we get with Class A, according to the RFC standard, is that the first bit must always be 0. What that means is if we were to look at our binary conversion chart, the first bit will always be 0 no matter what. So we can almost draw a line here, and the rest of the bits, once again, we have our starting bit, which is also known as the network address, and we also have the ending address known as the broadcast address, where we have all ones. What that means mathematically, though, is that the Class A starts at 0 and goes all the way up to 127. And let me explain what that means. You see, all the bits when they're 0, right? That means that Class A starts at 0. And because the first bit must always be 0, even for all the ones, the first bit is set to 0. But we have to add up all these numbers here, right? So let's quickly add up. What's 64 plus 32? That's 96. What's 96 plus 16? That is 112. And what is 112 plus 8? That is 120. If we were to add 4, that's 124. We add 2 plus 1. Add 3 to it, that's 127. What we get when all the bits are set to 1 is 127, as shown by the math here. However, as you can see here by these 2 asterisks, if we were to look at these 2 asterisks down below, all zeros and all ones are invalid host addresses. So that is something very, very important to keep in mind. And I'll continue explaining as we move forward, in case if it doesn't make sense at the moment. Now, another thing you want to look at is in Class A, the first octet is dedicated to networks, and the last 3 octets are dedicated to hosts. And the default subnet mask is 255.0.0.0. And here, the total possible number of networks is 2 to the power of 7. That's 128 networks. And within each network, we can have a total of 2 to the power of 24, which is 16.7 million plus hosts per subnet. That number is insane. What we have next is Class B. Class B starts off where Class A ends. So you see it starts off at 128. But before I go there, let's focus on the binary. So the RFC 791 standard defines that the first 2 bits must be set to 1 and 0. So let's go back to our binary conversion chart again. And we're going to be doing that a lot in today's session. So you get a pretty good feel for how this works. Because the standard says for Class B, 1 and 0 are always set this way and are unchangeable, we're gonna put them down like that. And another thing we want to keep in mind is, once again, our range always starts with all zeros and it ends with all ones. And then we have different combination of zeros and ones in between, right? This could be 1, this could be 0, so on and so forth. And what that means is, as you can see, the first value here is 128, right? And that's why our range starts at 128, as shown here. And down here at the bottom below, if you were to add 128 to all these different numbers here, let's do that. So 128 plus 32 is 160. 160 plus 16 is 176. Plus 8 is 184 plus 4 plus 2 plus 1. We'll just say plus 7. That right there makes it 191. So this is where the range ends, 191, and voila, it matches this value right here. So hopefully now you guys are starting to see a pattern here. Now, once again, in this one, in Class B though, 2 octets are dedicated to networks and 2 octets are dedicated to hosts. The default subnet mask for Class B is 255.255.0.0. Here we have a total subnets of 2 to the power of 14, that's 16,384, and we have total hosts of 65,534. The reason we have this -2 in the end, as you guys are seeing here, is because, once again, all zeros and all ones are invalid host addresses, meaning none of the network devices, routers, switches, IP phones, desktops, laptops, you name it, any network device in your network cannot be programmed with all zeros and all ones as the host address, because these values are reserved by the RFC to be able to identify the network address and the broadcast address. Next, we look at Class C. Here in Class C, the RFC 791 standard says all the bits in green, the first 3 bits must be 110. So once again, going back to our binary conversion chart, what that means is the first 3 bits will always be 110 regardless, right? So if we were to draw a line like this, because we cannot change the first 3 bits, let's see how the rest of it pans out. Well, I'm missing a 4 here. So what we'll have is 0, 0, 0, 0, 0, and we'll have 1, 1, 1, 1, 1 as the ending. So once again, top one is the starting position, and the bottom one is the ending position. And if we were to do the math, what we'll get is 128 plus 64 is 192. And this is what this value represents. This is where Class C starts. Where Class B ends is where Class C starts. And if you were to do the math here, with 128 plus 64 being 192, and then if you were to add up all these other numbers, it's going to end up being 2, 2, 3. And once again, that very conveniently matches where the Class C range ends. Class C has the first 3 octets reserved for networks and the last octet reserved for host. And the default subnet mask in Class C is 255.255.255.0. Here we have total networks of 2 to the power of 21, over 2 million networks, but we have hosts of 2 to the power of 8 minus 2, which means 2 to the power of 8 is 256. But once again, we cannot use the first and the last in the range. That gives us a total of 254. And that's what we're seeing here. Next up is Class D. Here, the RFC standard said the first 4 bits will be 1110. So going back to our handy dandy binary conversion chart, what you'll get here is the first 4 bits always locked in like this. And once again, our starting range starts with all zeros and ends with all ones. If we were to add up all these numbers, wherever we see 1, we add up those numbers, right? So 128 plus 64 plus 32 gives us 224, which matches the beginning of the range. And the next up, the final, is the 111 and then a bunch of other ones, and the only thing that's missing is 16. If you were to add all that up, that adds to 239, which matches this number right here. Now, one thing I want to mention about Class D is it's a unique class of IP addresses in a sense that it's reserved for multicast routing. And multicast is a whole different way of doing routing in our networks. Typically, when we talk about routing, we're talking about unicast routing. Here, these ranges are dedicated, this whole class D is dedicated to multicast routing. And in this course, we'll touch base on multicast a little bit. We'll talk a lot more about it in the CCNP class. So it's kind of beyond the scope of the CCNA exam, but you need to know a little bit about the multicast, which we'll cover later in the course. And finally, we have Class E. Here, what we get is, according to the RFC standard, first 4 bits are always set to 1, and then once again our starting position is all zeros, and then the ending position is all ones. If you were to add up all these numbers, all these ones to the left, you'll get the value of 240, and if you were to add up all the ones, of course you're going to get 255 as the end of the range. This is once again a unique bird in a sense that it's an experimental range. So in real world, you'll never see anything in this range being handed out in your network. So in reality, you should only see the top 4 classes of the IP addressing in your networks, and you shouldn't really see Class E specified anywhere. Now let's quickly talk about Classless. So we just finished talking about Classful IPs. So remember those different categories, Class A through E, we just finished talking about. This is the other side of it, where we have what's called a CIDR, or Classless Internet Domain Routing, or VLSM, or Variable Length Subnet Masking, where we have the ability to be able to control IPs. And this technique was introduced to slow down the rapid exhaustion of IPv4 addresses, because as I mentioned, we only have roughly under 4.3 billion IPv4 addresses, and we have to be smart about how we allocate and use them. And like I said, gives you full control as an administrator to use this space and then define and carve out the network portion and the host portion as you see fit. An address in a CIDR notation is written as follows. So you may see an address like this. Even though it belongs to Class A, you might say, well, if it's Class A, it shouldn't end with a /16, right? It should actually, Class A ends in a /8. And the reason Class A ends in a /8 is because, if you guys remember, the subnet mask is 255.0.0.0, which means only the first octet has all the bits on, and then the rest of the octets are all zeros. That's the default class. But that's not what we're seeing here. So what's up with that? Well, this is what's called classless, where we're taking an IP and we're carving it out according to however we want to carve it out to program our devices in our network. And what we have here is the portion to the left, which is the IP address or the network address here, 10.1.0.0 is the network address. That's what's called the prefix or the network address, and the /16 represents the suffix or the subnet mask. And this subnet mask in decimal would be written as 255.255.0.0. That's how /16 is represented. Now let's quickly talk about IPv4 private versus public IP addresses. So what had happened was, because as I mentioned, IPv4, there was this real scare many years ago in the IT community about running out of IP addressing space. And it's real, right? Because we have a lot of devices, a lot of people online, and we're running out of IPv4. So we had to come up with some clever, smart way of dealing with this situation. So what had happened was an RFC 1918 was published, and it defined what's called a private IPv4 address ranges. And these addresses can only be used on the LAN. They're not routable on the internet. And as a matter of fact, the service providers have filters in place to drop packets on their internet routers if the packets are sourcing from private IP address range, and I'll explain that momentarily. And here are the 3 private IP address ranges that you must memorize for the exam. The first range starts with 10.0.0.0 and ends in 10.255.255.255. It's a /8. It's defined in RFC 1918. The next range is 172.16.0.0 through 172.31.255.255. It's a /12 or 12-bit. And the third one is 192.168.0.0 through 192.168.255.255. That's a /16. If you see these IPs configured on your devices, then that means that your devices are configured to take advantage of private IP addressing space. As a matter of fact, I would be willing to bet that most of the environments that you are aware of today, including your home network, a coffee shop, your office, whatever have you, you're going to see IP addresses in one of these ranges. Should never be outside of these ranges. Unless you're talking about a data center where you have servers and things of that nature. Even servers shouldn't actually have public IPs configured on them. You would actually configure private IPs on the servers and then use another clever technique that we'll talk about in a moment to magically mask the private to the public IP. But the bottom line is that these are the private IP address ranges that you must memorize, not only for the exam, but it's a very real-world topic because that's how you configure your LAN or local area network. And as I mentioned, what ends up happening is if you're using these private networks in any of these ranges, 192.168, 10.0, or the 172.16 range that we talked about, as those packets go out and they hit your ISP router, right? So this could be, for example, your Comcast device at your home. This could be your cable modem. And then behind your cable modem, of course, you'll have your router. If that router that you have at home sends this IP, 192.168, 1.0, out to the ISP router, the ISP router will actually discard this packet. It's not going to send it forward. Reason being, these are private IP address ranges. They have no business of being available on the internet because, like I said, the RFC standard specifically called out that these IPs are not allowed to be routed on the internet. So they do not route on the internet. They cannot become part of the internet routing table. So you have to get creative to do something about it. And let me show you how we can get past this challenge. This is where NAT comes in. And NAT stands for Network Address Translation. And what that does for us is allows network devices on the LAN to be able to communicate over the internet. And the whole trick is that NAT function is ran on a router, could be a firewall, mostly a router. And what it does is it changes the source address in the IPv4 header. So if you guys recall the IPv4 header, right? It's 32-bit in length. We just talked about, the 32 bits and how they're carved out, and all the IP addressing we've been discussing so far is part of this right here, the source and destination addressing element. But what I want to point out is we need to swap out this private IP on our LAN that you're seeing to a public IP that we're going to get from our ISP, which means when the packets leave this router is going to run a NAT function, and it's going to translate and swap out this private IP with the public IP. So when the packet gets to the other side, they never see the private IP. All they see is the public IP. And this fools the ISP router. Now, if we were to talk about the ISP router, which is right here, when it gets this packet, when the source address is public, well, this router has no problem because it's designed to forward public routes. So it's going to forward the packet. But if you guys recall on the previous slide, the reason the ISP was actually discarding the packet before using NAT is because it's programmed not to allow the private IP addressing space to be routed across the internet, because that's what the standard says. Now, quick disclaimer, I'm not going to go deeper into NAT here because this section is about IP addressing, but we'll have another section later in the course under IP services where we'll go deep into this topic, and we'll talk about the static and dynamic and different types of NAT strategies that we can use to be able to configure our network. But at this point, I think this is sufficient enough information for you to understand the concept of NAT. Now, let's go through a bunch of different exercises so you get to learn how subnetting actually works. The VLSM, the variable length subnet masking. How does it work? How do we take an IP address and kind of chop it up into different networks? Well, here's the first example where we've been given this IP address up at the top, 200, or network address I should say, 200.10.5.0/24, and we've been asked to create 4 subnets out of it. Well, how are we going to do that? Here's a 3-step process that I love to use, and there are a number of different ways of doing it. And I don't blame you if you end up using another method if it works better for you. But the method that works best for me and for my students is this one. They absolutely love it, and I personally also loved it when I was a student myself. So the first thing we do is we convert the number of subnets required from decimal to binary. So what are the total number of networks required? You need 4. So what that means is we talked about, if you guys remember, handy dandy binary conversion chart, right? 1, 2, 4, 8, 16, 32, 64, 128. Now, if you need 4 out of these, we have to see how we can come up with number 4. Well, if this bit is on and if all of the rest of the bits are off, that gives us a decimal value of 4. And that's exactly what we are after. Now, what we do next is we defined the network bits to create a modified subnet mask. So the default subnet mask we have in /24, by now you guys know, is 255.255.255.0, which equals a bunch of 1s in the first octet, a bunch of 1s in the second octet, a bunch of 1s in the third octet, and all 0s in the fourth and the last octet. Well, we learned from the previous step that it takes 3 bits to produce 4 networks. What that means is we're gonna go ahead and borrow 3 bits from the host address. And just to quickly clarify, in /24, the first 3 octets are all network octets, right? They're dedicated to networks. And what we need to do is we need to find 4 networks, right? So what we did was this right here is the host octet, the final one. We borrowed 3 bits that match the 3 bits that we came up with here, right? To come up with the value of 4. So that's what we're doing here. And what that gives us is a modified subnet mask of 255.255.255.224 or /27. Why do we call it /27? Well, if you were to add up all these bits here, all these network bits, and by the way, network bits must be contiguous. If they're not, that's a violation of the IPv4 addressing rules. So make sure that, in other words, you can't have a network where you have a 0 here, for example, and 1, and then 0 and 1. You will never run into a situation like that ever, because that's a violation of IPv4 addressing rules. When you have all 1s like this, you should always see contiguous ones, okay, in all of these octets. So something for you guys to keep in mind. And the 224 value is, once again, looking at the binary conversion chart where we have 1, 2, 4, 8, and all that, right? This is 128 position right here. This is 64 position. This is 32 position. If you add all that up, that equals 224. Third and the final step is we define the network range for each subnet. How do we do it? Well, we focus on the last network bit. So if you guys remember, this was our last network bit. This last network bit position, what's this position here? Let's blow it up a little bit. So we have 1, 2, 4, 8, 16, 32, 64, 128, right? So if I were to do 1, 1, 1, 0, 0, 0, 0, 0. Well, this right here is the last network bit position. That's what I'm talking about, right? Which is 32. The value 32 comes from here. It's the least significant bit. By the way, that's another terminology you guys need to be aware of. The leftmost bit is considered the most significant bit, and the last network bit is considered the least significant bit. So we'll look at the least significant bit value position, and we'll take that from the modified subnet mask, which we're looking at right here, to define our network range. So the first range ends up becoming 200.10.5.0 through 200.10.5.31. Well, how did we figure this out, and what are we doing again? Well, let's take a step back quickly. What that means is, after modifying what we needed to modify in order to get 4 networks, right? Create 4 different chunks or 4 different pieces of this network, 1/24 divided into 4 different subnets. We did all this to come up with certain values, right? And if you were to pay attention to this right here, the modified subnet mask, that tells us everything we need to know. And here's what I mean. All the network bits that we have, if you look at all the zeros, these are for hosts. How many zeros we have? 1, 2, 3, 4, 5. We have 5 zeros, right? So 2 to the power of 5 gives us what? 32. That's what it gives us, right? And that's the value that we're looking at here. So what that means is we'll have 32 hosts in each subnet. And if you guys remember, we have to do 32 minus 2 to get to the value of 30. That's the usable space. That's what we call usable IP address space, because we cannot use the first IP because that's the network address, and we cannot use the last IP because that's the broadcast address, and these are reserved according to the RFC standards. So what does that mean? What should be the next range here? Well, what that means is the next range should start with 200.10.5.32, because this value is 32 here, right? And at this point, I think we can start identifying that the one after that would be 32 plus 32 is 64. And then if we were to add another 32 to that, we'll get 96, and so on and so forth. These are all the different ranges that we'll actually end up getting. So we're gonna get, instead of 4, even though we needed 4, but the way it worked out, we're gonna actually end up with 8 networks. And these 8 networks, each network is gonna be able to support 30 usable IPs. And where does this number 8 come from? Remember the borrowed bits. What's 2 to the power of 3? How many bits we borrowed? 3, right? That's 8. These are the networks that we're gonna end up getting. So as you can see, once you guys understand and get a feel for this binary conversion chart and math, it kind of becomes very cool, and you sort of like become a ninja of going back and forth and doing conversions between binary and decimal to make sense of what you're dealing with. So I've got a ton of other examples. Let's keep rolling. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.